Well, hello and welcome again to our journey into complex analysis, and we're up to section 6, which is on Cauchy's theorem. So thus far we've seen that if you've got a continuous function f, if it has a primitive, and that's a big if, then the integral of f on a closed contour is 0. What we'd like to do is to find a simple condition on f to guarantee that it has a primitive. And it turns out, as you might hope, all that we require is that f be analytic. We're not going to prove this result in its full generality. Koshi was able to prove this result, as we will, by assuming that f dashed is continuous. This restriction was removed by Gurusar, who lived 1858 to 1936, and so the theorem, which is the basis of complex integration theory, is often referred to as the Cauchy-Gurusar theorem. And we're only going to prove the result on the assumption that f dashed is continuous, but you can look up more advanced books and you'll see a full proof of the Cauchy-Gurusar theorem. Firstly, we say that a domain D, that's a subset of the complex numbers, is simply connected if every simple closed path, that is one that doesn't cross itself, in D encloses only points of D. So that means points within a circle or a square or a polygon are examples of simply connected domains, while the set of points in an annulus is not. Because if you take the closed contour around the enclosing the inner circle of the annulus, then it no longer encloses points entirely in D. Now you'll need to recall here, I'm going to use Green's theorem. You may recall Green's theorem in the plane from earlier several variable calculus courses. If not, then I'll just restate it here. It says, suppose that we have real functions u of xy, v of xy, along with their partial derivatives, and we need those to be continuous throughout a simply connected region R, consisting of points interior to and on a simple closed path C, positively oriented, that is generally anti-clockwise. Then Green's theorem in the plane says that the integral, the line integral along this curve C of u dx plus v dy is given by the double integral over the region that this C contains of this quantity here, partial dv dx minus partial du dy in the dx dy. So this connects what's happening on the boundary to what's happening on the interior. It is in some sense a generalized form of the fundamental theorem of calculus. And of course, if you go on to study more of several variable calculus, you'll see also Stokes's theorem as a similar generalization. You'll also notice, of course, that this looks a little bit like a determinant in some sense, and in fact that's where it comes from. So Cauchy's theorem, well, I'm really stating Cauchy-Gurusar theorem. If f is analytic in a simply connected domain, then if you've got a simple closed path C in this domain, then the integral of f around C dz is 0. So as I noted above, our proof will also require f dash to be continuous, but I've suppressed that from the statement of the theorem, since it can be dispensed with by using a more sophisticated proof. Now here's the little proof of this using Green's theorem. So we're going to write f of z as u plus iv and dz as dx plus I dy. Then if I go to evaluate this integral, I can replace the f with u plus iv and the dz with dx plus I dy, and I can split this up then into two line integrals, each integral itself being real. Now, assuming that f dashed is continuous, then that means u and v have continuous partial derivatives. So I can apply Green's theorem and I can replace this thing then with minus the double integral of dv dx plus du dy, and then plus I times partial du dx minus partial dv dy. So I'm simply using Green's theorem in the plane to write down these integrals. And you see I'm replacing the u remains as u up here. The v in Green's theorem gets replaced with minus v, and hence I pick up an extra minus sign, and here the u and the v remain the same as in Green's theorem. In fact, that's what happens there. So we end up with this when you substitute it in, and R is the region which is simply connected and in D enclosed by C. But now by the Cauchy-Riemann equations, each of these brackets is 0, and the result follows. So there it is. Comes out easily once you use Green's theorem, but that of course assumes that f dashed is continuous. This would not be the way Koshi originally did it, but perhaps in a similar way. So, since any path which is closed and has self-intersections can be decomposed into simple paths, so if I've got some sort of contour like this that crosses itself, well, I can chop this here, and I can think of this one here as like one contour here, and this one here as another contour here. And so by that decomposition, we can see that Cauchy's theorem holds for all non-simple closed paths, for a non-simple closed path with a finite number of intersections. Now, two important applications of Cauchy's theorem. The first one is we really want to know when a function has a primitive, and we can now answer that question by using Cauchy's theorem. So if f is analytic in a simply connected domain D, then there exists a function capital F which is analytic in D, so that capital F dashed is little f. So again, then if we have an analytic function, it has a primitive. Might not be one that's easily calculable or computable, but it has theoretically then a primitive. So we pick, the proof's a little bit fiddly, so we pick a fixed point z0 in D. So here's our domain D. And we have a point z0 inside here. And we pick any other z in D. And we're going to define this function capital F of z to be the integral from z0 up to z of f of zeta d zeta, where the integration is along this straight line from z0 to z. Because this is obviously going to be our hope that this is the proper primitive for this function f. So I'm going to define this now to be the integral, the line integral, along this line from z0 to z. Now, since z lies in D, and D is our domain, then there is a neighbourhood of z lying in D, and so that means I can take, if h is a complex number with mod h sufficiently small, then z plus h lies completely in D. And the line segment between z and z plus h also lies in D. Since D is simply connected, the line segment from z to z, sorry, z0 from z plus h lies in D. And so by Cauchy's theorem, I can add up the three integrals. So I can integrate from 0 up to z plus h, and then from z plus h to z, and from z to z0. And when I add those ones up, if I integrate f on the sum of those, I have to get 0. Now if we look at what that says, then the integral of f of zeta from z0 to z plus h Well, that's just capital F of z plus h by our definition. And the integral from z to z naught, well, that's minus the integral from z naught to z. So that's minus capital F of z. And that leaves this one in the middle, and I can flip the endpoints around and take that on the other side. And so I get this difference then is the integral from z up to z plus h of f of zeta d zeta. So I'm obviously going to, this is looking like a difference quotient, so I'm going to divide both sides by this h that I defined above. And then this difference quotient now is just 1 over h times this integral. So if h is not naught, and I'm assuming here h is not naught, so if h is not naught, I can subtract f of z from both sides of the equation, and I can take the minus f of z inside the integral because it's just a constant. And the integral of this from z to z plus h is of course h times that, and then the h's cancel, so that's why I can take this inside. Now, since f is continuous, given any epsilon bigger than 0, f of zeta minus f of z is less than epsilon whenever zeta minus z is less than delta for some delta bigger than naught. And so I can then get a bound on the size of this thing. Hence, I can squeeze this in here. Putting this together then, I can then say that this difference quotient is less than my epsilon, because this thing here is less than epsilon, so I can integrate epsilon between z and z plus h, which just gives me h. The h's cancel, and so I just get this as less than epsilon. And this is for any epsilon bigger than 0, and of course that's the definition for for the derivative of this function to be this function. In other words, capital F is a primitive for little f. Now the second application, which is also very, very useful, is to the defamation of paths. So in general, our part C of integration may be very complicated, but we would like, under certain conditions, to be able to replace a complicated path C by a more straightforward path without penalty. And I leave you with a little challenge problem that if you've got C and C dashed are simple paths from Z0 to Z1 enclosing a simple region R, and if F is analytic in the domain containing domain D containing R, then you're invited to prove that the integral around C equals the integral along C dashed. And that's not very hard to do. In fact, you simply integrate along C and then go along C dashed backwards, and that'll give you a closed contour. The integral of that is 0, and then you can just simply, this will fall out. So that's an easy exercise there. Now our main theorem is that if gamma 1 and gamma 2 are two simple closed contours, both oriented anti-clockwise, and we're given that gamma 2 lies inside gamma 1, and that f is analytic between and on gamma 1 and gamma 2, then the integral around gamma 1 equals the integral around gamma 2. We're looking at a picture here. There's my gamma 1, there's my gamma 2. We're assuming that the function is analytic in between the two, and this theorem says that the integral around gamma 1 is equal to the integral around gamma 2. Now gamma 1 could be some very complicated looking contour, not just a circle or something. It could be some very complicated contour, and gamma 2 can be a nice circle, and this is saying that I can deform this integral down to this integral along the with respect to these two contours. And that's going to enable us to replace a complicated contour by a much simpler one. And provided we've got analyticity between the two contours, then the two contour integrals will be equal. And the proof's actually really easy. It's a lovely example of a little bit of topology with some complex analysis. So keeping the region between the contours on our left, so as I'm moving around here, I'm going to traverse, and I'm going to put capital gamma to be, I'm going to go along gamma 1, and then I'm going to go, this one here is going to be called alpha, so I go along gamma 1, I'm going to combine that with alpha, then I'm going to go, keeping the region in between on my left, I've got to go that way, and that means I'm moving along minus gamma 2, so I get back around to here. Then I go back along minus alpha in that direction, and then I finish off my gamma 1 back to start again. So I can write this contour gamma, capital gamma, which is gamma 1 union alpha union minus gamma 2 minus union minus alpha, and that's giving me a closed contour. And that means because the function's analytic between the two, that is in this region on my left, then the integral around capital gamma is 0 by Cauchy's Gurusar theorem. And now I just add up all the contours. So I've got the integral around gamma 1 plus the one on alpha minus the one on gamma 2 because I went the wrong way, and then minus the integral along alpha because I went the wrong way. These cancel out, and the result now follows. That just says the integral along gamma 1 of f equals the integral along gamma 2 of f. So that's a lovely result there. And that might do for this particular video, and in the next one we'll finish off this chapter.